now. She always says that. I hope that's okay with you. So we're going to go back and, oh, hello, Dandora. Good. Excellent. That is a great shirt, teacher. That is a fabulous shirt. Oh, they've gone. It was too good a shirt. You see, you get a shirt like that and your video doesn't work anymore. The
Oh,
camera
thank you.
the camera is so surprised by the shirt.
Oh, thank you.
It's a great shirt. Right. Okay, guys, here we go. So, energetics. We're going to continue with energetics. We're going to go back. The last two bits were latent heat of changes, and also then how you do experiments. This is for paper 3 as well as theoretical. Okay, so I'm going to share my screen now. For everybody, if you have a piece of graph paper for a little bit later, that's great. If you don't worry, it's okay. All right, so I'm going to share my screen now. I'm hoping to share my screen. Where has my video gone? Oh, here we are. Aha. Okay. So, whoops. Okay. So here was part of the slideshow that I showed you last time. And we said about solids, liquids, and gases and the difference between them. Solids very close together, regular arrangement, not necessarily like this, and they just vibrate on the spot. Liquid, close together, but random, quite difficult to draw really close together, but random, and they move around each other, but still trapped in the body of the liquid. Gas, much further apart, random arrangement, and they move quickly. Now, this doesn't say about the force between them, but I said last time, the force between the particles is the same in all pictures. But when they are moving only slowly in the solid, they can just vibrate, and the solid, the particles are held together very strongly. In the liquid, the forces are still effective, so they can't get away too easily. But in the gas, the forces are ineffectual. So I thought I'd show you something else, which I hope will help in this. Where's it gone? Ooh, I've lost something. Hang on. Okay. This is, let us imagine that we are looking at a solid, two different types of atoms, and let's put them in a box, well, in a beaker. And the particles are just moving very, very slowly, okay? They are vibrating on the spot. If you look at them, they are very close together, but the forces of attraction are shown by the little white lines. On the left, I can increase the temperature. I can also make them vibrate faster, but I'm not going to worry about that. So I'm going to increase the temperature. And as I increase the temperature, the kinetic energy increases. Kinetic energy is just, in this terms, movement of the particles. They can't get away from each other, and therefore they are held by the forces of attraction, and that means that then they can't get away, but they vibrate more violently. As I increase the temperature a little bit more, what happens is that they still can't get away, but now they are starting to vibrate a lot. The forces of attraction are the same strength, but because the particles are moving more violently, the forces are finding it more difficult to keep them together. I'm going to increase the temperature more. As I increase, excuse me, the temperature, what we find is that the particles start to move in such a way, the kinetic energy increases, continues to increase, until they start to disrupt the forces of attraction. So here they're not quite as organized as they were. They are still a solid, but they are becoming a liquid. They are becoming less organized. There they are now a liquid. Now, as they're liquid, some of them may be able to escape for some of the time, so to evaporate. So you will see ones occasionally break off and go off for a moment and then come back, like that one. Now, sometimes they do not come back. So as I increase the temperature, so the kinetic energy has been increasing until it starts to overcome the force of attraction. Now I'm going to increase the temperature some more. So we now have a mixture between solid and liquid. And I'm increasing the temperature. And now more of the particles are starting to escape, perhaps in pairs, perhaps individually. Now it is evaporating or possibly boiling, depending on the temperature. Now the forces of attraction are not strong enough to hold the particles together. So the kinetic energy now is quite high, but you can still see some of the particles have forces forming between them and staying for a little while. As I increase the temperature, there comes a time where the forces of interaction, the forces of attraction, cannot hold them together. So even if they have a moment together, they will fall to pieces. I'm going to get rid of the beaker now. Now, if I cool them down, what happens is that the particles start to move more slowly. And as they start to move slower and slower, the forces of attraction start to be able to take over again. And you can start to see that more particles are starting to be actually attracted to each other. Not enough yet. They are still a gas. The particles are still moving too quickly, but now they are starting to slow down, and now the forces are starting to take over again. Because the forces are taking over again, now they are getting organized, and the forces are starting to win now compared with the kinetic energy moving the particles about. So let's just restart. At the beginning, the particles are in a regular arrangement. The particles are held by the force of attraction and can only move on the spot, vibrate on the spot. If we increase the temperature to the point where it becomes a gas, there are still forces available to the particles. They are still attracted to each other if they come close enough. But the kinetic energy is high enough so the particles cannot stay together. So as they come together just for a moment, particularly if they are slow, you may notice some of the particles here are moving much faster than others. This one here, blue one here, is moving very slowly at the moment, but after a collision, it may move much faster. So in a set of particles at any temperature, some are moving faster than others. So the kinetic energy depends on the temperature, and the effectiveness of the forces depends on the kinetic energy. I've now dropped a gas. I've dropped its temperature to the point where it's going to deposit. Remember, straight from gas into solid. This is deposition. The opposite of that is sublimation. So these particles are now becoming solid, regular arrangement, and therefore that's a solid. Sometimes it's easier to see it in just one set of colors, but it doesn't make much difference. So if I see it in one set of colors, I can go for sublimation, looks like this. The solid becomes a gas without becoming a liquid. That's sublimation. And deposition is exactly the opposite, going straight from a gas straight into a solid. It's quite attractive, isn't it? It's quite nice to watch. It is good for your brain to just go, it has been a hard day at school. Now I can just go to sleep watching little green things attract each other. Okay, So I hope that makes sense. I'm sorry to wake you up again. Sorry. So in this picture here, this is what this is showing here. Solid, liquid, gas, that's the sort of thing you might have to draw. And kinetic energy would go from very low in the solid into the liquid, into the gas, more and more kinetic energy. We said that we could draw that in graphs like this. So time along the bottom and temperature up the side, and it goes that all the solid can be heated up along this diagonal line at the bottom. Here, I don't know if you can see my pointer, but where it says solid here, starting at the axis, and it goes up diagonally, that is the solid just heating up, and then the energy goes into increasing the kinetic energy until it starts to break the bonds. When it's breaking the bonds here in the horizontal bit, this is what we call melting. So we have solid, then solid liquid, and then boiling, liquid gas mixture, and then just gas. Okay, so that is a useful graph, and it's important that you are able to understand that. There are two types of question which come out of this type of graph. Let me show you them. So if some people there, I think, are just sketching that, I'll just give you a moment. I'll just give you a moment just to sketch that, and then we'll move on. This time along the bottom could also be kinetic energy. Sorry, temperature up the side could also be kinetic energy. It means the same thing, except that in this horizontal bit, the kinetic energy is still increasing, but it is simply going into shaking the bonds apart. Now, this sort of graph is true for all substances which melt and boil. It would not be true for those which only sublime. For instance, if I have carbon dioxide, unless it is pressurized, goes straight from solid into gas. So in other words, we will get a line that goes up diagonally and then horizontally and then diagonally, but there would not be two horizontal bits. Okay, so I'm moving on. So sometimes they ask a question. Ready for me to move on? Okay, you've got 1 minute. Use the time not to show your thumb, but to draw the picture. Okay, moving on. So next picture. Now, sometimes they ask you what is happening between, for instance, A and B, or between C and D. So you have to be able to tell them. So if I said, what is happening between A and B? Well, I've got to remember that is all solid. So that's solid. This is melting between B and C. Between C and D is the liquid heating up. Between D and E, it's boiling. And between E and F, we're heating up the gas. So if they said, what is happening to the particles between B and C? You would say, at B, they were all solid and the heat is increasing, but all of the energy is going into breaking the bonds and it is melting and turning solid into liquid. If they asked me what was happening between C and D, I would say, hey, this is all liquid and the liquid particles are moving faster and faster and faster and faster, but they are all within the same liquid. Okay. The second sort of question is, what is the boiling point of this chemical? What is the boiling point of this chemical? Well, this is melting, B is melting, D is boiling. So I would draw a line across here and say, well, it looks to me like it's 61 or 2 or something like that, just over 60. Okay? If they ask you for the freezing point, you go, this is the melting or freezing point, that's minus 60. Okay? Sometimes you come across a question which uses a chemical you already know about. This chemical has a freezing or melting temperature of 0 and a boiling temperature of 100. It is most likely to be water, but many of them are not. Sorry, this one here, minus 60 and 60. Minus 60 and 60. They can also show you a graph the other direction. This is one being cooled down. So you have to think, okay, I need to reverse this in my head. So the coldest temperature down here, this must be solid. So this here must be freezing. This second flat bit here must be freezing. And this here must be condensing. So up here, it's a gas. So in other words, its boiling point is 120. It's sometimes easiest to think it as though it's going the other way, as though it's going from right to left. So this is solid heating up, then horizontal here. This would be melting. This is the liquid. This is boiling, and that's a gas. Okay, so they could do it that way round. It's unlikely. I have not seen a KCSE question like that, but it could happen. Okay, so sometimes they ask you whether something is a solid, liquid, or gas at a particular temperature. And the normal temperature is room temperature. Room temperature is 25. So all you do is to draw a line from 25 across, and you see which part of the graph interacts with it, and you say, it's that bit, solid, solid, liquid, liquid. So this chemical at room temperature is a liquid. Okay, important that you can do that. Okay, the last bit of enthalpy is about measuring and calculating enthalpies. It can come up as a practical, and I will show you a practical in a minute, but it's about measuring them and calculating them, and you will need your graph paper in a moment. So here we go. This is about exactly that. Okay, so most of these sort of experiments heat up some water. And all of the heat either given out or taken in changes the temperature of the water and therefore the thermometer. So the thermometer is telling us the change in the temperature. The volume of water is needed. The volume, it's actually the mass of it, but it's easier to think about volume. You'll see all of these in a calculation in a minute, so there's no need to write this down. No need to write it down yet. You will be given what we call the specific heat capacity of water. This is the amount of energy in joules that you have to put into 1 gram of water to raise it by 1 degree Celsius. You will be given this. You do not have to remember it. It's about 4.2. This is what you need. If you're going to write anything down, I would write this down. If you don't know it, if you know it, don't worry. So the heat lost, in other words, given out or taken in the reaction is the mass of water, excuse me, times the specific heat capacity of water, that number you will be given, times the change in temperature. This is sometimes called Q. There's no need to remember Q. Just remember that the total energy change is the mass of water times the specific heat times delta T, the change in temperature. If you already know that, that's fantastic. How many people already know that? If you already know that, just show me thumbs up. If you already know that, Dandora says yes, Usharika say yes, and Samari say yeah. That's great. Brilliant. So here we go. Now, we need, most of the time, we need the molar enthalpy. That's the energy given out per mole. The molar enthalpy is that energy there, Q, divided by the number of moles which have reacted. Okay, so it's the mass of water times specific heat times the change in temperature all over the number of moles heating it. So let's have a look at a question. Oh, firstly, this is how it's done. Very simple. This is something you might need to do. In paper 3, you sometimes have to do this, and sometimes you have to mix two chemicals together in the water. It doesn't make any difference. The thermometer is taking the temperature of the reaction. So let us imagine that we are trying to find how much energy is given out by an alcohol. There are lots of many alcohols, or alkanols, as they're called. Alkanol or alcohol is the same title for that family of chemicals. So we have a certain amount of water. We need to know the amount of water. We need to know the thermometer at the beginning and the end, and we need to know the mass of alkanol which is burned. Here is a little experiment. Oh, why is that not working? Ah, it is. Here's a little experiment I'm going to just show you very quickly. It's not terribly interesting. It's just in case you have to do something like this. Now, you don't need all the equipment that this shows you. You could do this with a Coke can and put the water in that. It's more effective than these. This is called a copper calorimeter. It's like a beaker made of metal, so it conducts the heat better. But a Coke can is just as good. All you would need is a thermometer, some way of measuring the volume of water, and some way of weighing whatever is being reacted. So here it is. I'll turn the volume off because there is no need to listen to them. Okay, very simply, they take a spirit burner. They're trying to find it for hexanol. Okay, so they put the hexanol, they weigh it down, and it is really important that you measure everything at the beginning. So in this case, they've got 129.56 grams of the hexanol in the spirit burner and the lamp, the wick. They measure out, that says 100 cubic centimeters of water. You can't read it on this slide properly. It doesn't matter. And they put that into the copper calorimeter. Now, what is important here is that they let it sit for a moment so that before they put the thermometer in, they let it get to the same temperature. So the water and the copper beaker and so on are all at the same temperature. Now, they have got a little lid on it, the top for it, to stop any heat being lost. They also have a little behind her fingers there. That is a little piece of metal which will help them stir the liquid inside. So they take the temperature at the beginning, and the temperature at the beginning is recorded. So here is the alcohol, and they're going to light it and put it underneath the beaker. Excuse me. And then they are going to stir it and take the temperature and so on. Now I'm going to run through because they do it for some time. Boring. Sometimes you have to wait for quite a while. But eventually you take the spirit burner and you put it out and you reweigh it. Now, what is important is that you blow it out at the moment, at this point here. Wait a minute. There. This lamp is still burning, but the heat is not heating the water. That is foolish, because that will be heat which is wasted. Okay, the heat which is just burning here is wasted. Now, they're now going to blow it out. Then they will take the final temperature and they will take the final mass, 129.2. I'll show you the results in just a minute. So now they have everything that they need. So let's just have a look at that. So we've got the initial mass of the alcohol, of the alkanol. We've got the final mass. Don't bother writing them down just for a minute. I'll show you the calculation. So they work out the mass used, which is 0.36 grams. The initial temperature was 19 and it went up to 29. Okay, so far, so good. And they had 100 cubic centimeters of water. Okay. Now, if you're doing this yourself, if you were going to do this practical yourself, a few things. One, make sure you measure the water properly. Number two, light the spirit burner underneath the Coke can or beaker, whatever it is. Do not light it outside, put it underneath. Weigh it very carefully before. When you blow it out, weigh it immediately because some will be evaporating. If you left it on the edge of the bench, of the table for a while, what will happen is the alcohol will just go. That's no good. We want to measure exactly how much alcohol burned. Okay, so let's have a look at the calculation. So hopefully you are able, whoops, sorry, wrong one. My apologies, wrong one. Okay. So here are the results here. Now, what we're going to do is we're going to do the calculation now. I'm going to show you the calculation just to make sure that everybody is happy with this. If you are already happy about how to do the calculation, then do it now. Just write down what you need, which is 0.36. It was hexanol. Hexanol is C6H13OH. C6H13OH. If you're happy to do the calculation, you just do it now. It had 100 cubic centimeters or 100 grams of water, and the temperature goes up by 10. I'm going to show those people who are not so sure. So here we go. Let's just, sorry, hang on. Come on. Come on, come on, come on. Sorry. Why is this happening? Oh, how very peculiar. Wait a moment. There's something funny happening with my projection. Okay. So how we do it is this. So the total heat change is the mass of water times the specific heat capacity which you are given times the temperature change. So that is 100 grams because it was 100 cubic centimeters times 4.2. Sometimes it will be 4.18. It doesn't matter. You just put whatever value you are given times 10, which is 4,200 joules. You could turn that into kilojoules here if you wanted, 4.2 kilojoules, but doesn't matter. Now we need to work out the number of moles of hexanol. Now, the hexanol, if you work out hexanol's RMM, it's 102, 102. So the number of moles of hexanol are grams over RMM, which is 0.36 over 102, which is 0.0035 moles. 0.0035 moles approximately. The total heat is Q over N. So that's the total amount of heat given out over the number of moles. So it's 4200 over 0.0035, which gives us this large number here. This large number here, 1, 2 with 5 zeros, but that's in joules. So I divide by 1,000 and it gives me the answer, 1,200 kilojoules per mole. Okay, so all I needed was the mass of the water, the value which they give me, the temperature change, and then divide that by the number of moles. It should be turned into kilojoules per mole, but that's it. Okay. Oh, come on, what's happening? All right. So here's one for you. Here's one that you can have a go at now. Okay. So I'd like you to have a go at this one. So 1.3 grams of ethanol, which C2H5OH, was burned. 1.3 grams of ethanol was burned. We heated up 150 grams of water. 150 grams. I'm going to take the specific heat capacity as 4.2, and it heated it from 24 up to 77. Okay, 150 grams of water, 24 to 77. I want you to calculate the amount of heat given out, the moles of ethanol burned, and then the enthalpy of combustion. Okay, have a go at that. I'll give you some minutes to have a go. Everybody have a go, please. I'm just going to go and get a glass of water. Oh, some people have got some answers. Negative 118. Well, we'll see. We'll see. Just check. Just check your answers quite a lot. Go through all of your answers, all of your calculation carefully. It's got to be negative because the heat was given out, but you think it's 121. Okay. 121. I'll go through the calculation in just a moment. I hope everybody's having a go. Sharika are going, why do I have to do this? I've had a hard day. Why do you make me do this? This is wrong. Come on, guys. Gotta get good at chemistry. Okay, so I'm going to show you how the calculation goes. Okay, so 1.3 grams of ethanol. I should have said C2H5OH, it's RMM. Well, it's 2 carbons, each carbon is 12. It's 6 hydrogens, they're 1 each, and 16 for the oxygen will make it 46. Okay, so the RMM, or molar mass, will be 46. So how do we do it? Well, we need the mass of water times the specific heat capacity times the change in temperature. That's 150 times 4.2 times 77 minus the start temperature. And that gives me 33390 joules. 33390 joules. Or 33 kilojoules. The moles of ethanol is grams over RMM. If you're not very good at moles yet, do not worry. I will help you with moles. So it's grams over RMM or MR, whatever you want to call it. You might call it the relative molar mass. It doesn't matter. It's the mass of 1 mole of ethanol, which you get by just adding up their atomic masses. So that's 1.3 over 46, which is 0.028 moles. Now, the molar enthalpy is that number, the amount of heat given out, divided by the number of moles. So it's 33390 divided by 0.028, which comes out as a huge number. But that's in joules. Oh, I'm sorry, that should be a capital J for joules. So I divide by 1,000 and the answer comes out as minus 1193. Negative 1193. Why is it negative? That's because it's exothermic. That's because it's exothermic. Now that's really important that you remember that anything which gives out heat will have a negative delta H. Okay, here's a real exam question, and I'm going to ask you to get your graph paper out and have a go at this. It says here, part 1, plot a graph of temperature on the y-axis against time. So we start with that. I'd like you to make sure that your temperature goes up a bit past 29 here, say up to 35 up the y-axis, okay? Now this is one not with a burner. This one here doesn't have a burner. It is adding some sodium hydroxide to some water. So they tell you that they've got the mass of a plastic beaker, that plus some distilled water. So you can work out the mass of the distilled water. And then they tell you when they've added the sodium hydroxide, that's the mass there. So the third number minus the second number will give me the sodium hydroxide, and the second minus the first will give me the mass of water. Okay, so, but start by plotting a graph, and what I'd like is everybody to have a go at this question. Now, if you know about extrapolation, you will need it, but if you don't worry, I will show you it. Okay, so I'd like everybody to try and have a go at this. This question, because this is very typical of what you have to do. Some of you will look at this and go, well, wait a minute. From my graph, determine the maximum temperature attained. Well, surely it's 29. Now, if you've been taught how to extrapolate back, you will know the answer is not that it is 29. It's something different. And what we've got to do is to try and plot the graph and work that out. Okay, so I'd like everybody to try and plot the graph and see whether you can work out what the maximum temperature attained is. And then we can look at the rest of the question. Okay, we can look at the rest of the question. So have a go, plot the graph. There are the numbers. It's quite quick because they're just going up in 30s, 0, 30, 60, 90, 120, and so on. And the temperatures are there. So please plot the graph first. It's just a bit of practice, but it's important. This is a real KCSE examination question, and it was worth about 5 marks. Hey guys, I'm not saying anything here on Valentine's Day, but somebody at Silver Spring has received a rose. Oh yes. Do you want to show us it? Come on. Come on, show us the rose. Come on, it's Valentine's Day. You got to show the rose. Come on. Look, everybody. Somebody's lucky. Oh no. Everybody else is going, oh, shut up. Everybody's going, I don't care. I have many, many roses. I don't like him, don't like her anyway. Yeah, that's a nice rose color, Glory. Well done. Silly. There, you're famous now. You see? You're famous for having a rose now. You're recorded for all time. You'll be on YouTube later because I always put these lessons onto YouTube. So I hope the graph is going okay. Some people can't concentrate anymore. I hope the graph is going okay. And then from the graph, try and find the maximum temperature which is attained. For those of you who are going Valentine's Day, hey, I don't care. Many of the roses which are given out in the UK are grown in Kenya. Isn't that amazing? Well, yeah. For those of you who are athletes, We were very, very saddened to see the death of Kelvin Kiptum, the world marathon record holder from Kenya, in a car accident. It was really, really tragic. So if you are old enough to drive, be careful. When you get to driving, be careful. Please. What a waste. Okay, I hope you've got a graph now and you now have the maximum temperature. Now you need to know the temperature change. You can work out the mass of sodium hydroxide used, and then you have to work out Q. That's the mass of the water, which is around about 100, times your temperature change, times, at the bottom here, it tells you that specific heat capacity is 4.18. In this case, they want you to use 4.18. Okay? Dandora, finished? Whoa, Dandora, finished, they say. They say they're finished. Has anybody got an answer? Show me, St Mary's. Show me, please. St Mary's had an answer there, I thought. No?
Is the temperature negative 16 or 15?
Sorry?
Is the temperature negative 16 or 15?
Oh, very good graph. Sorry, is the temperature what? Dandora, you asked the question. Is the temperature what?
Is temperature negative 15 or 16 on the first?
On the first one, yes, 15.
Yeah.
Sorry, is it difficult to see? I'm sorry. I'm just going to show you another slide in just a moment. I'm going to show you a graph of it using something fairly simple. But I will let everybody have a go first. Oh, great graph, Osharika. That's a lovely graph. So what is the temperature change? What is the total temperature change? That's a really nice graph. Well done. If you draw a graph, try to spread it out. If you don't spread it out, as we will see in a minute, the shape of the graph is a little bit wrong. or less easy to deal with. So try to spread out, try to use most of your graph paper. If you don't, it will be difficult to use. Show me your graphs when you've done them. Show me a graph. Let me have a look at a graph. Very nice, Dandora. Very, very nice. That's good. That's excellent. Now, how do we find the maximum temperature? Because it is not simply 29 minus 14, minus 15. It's not 14. Okay? This is really important. It is not that. We have to do some extrapolation backwards. This is a really crucial skill. I'm going to show you my graph now. I'm going to show you a graph which was produced using Excel spreadsheet. So you draw the graph, and most of you should draw a nice smooth graph, but I'm going to show you Excel because it helps us understand. Now, if I was drawing this graph properly, I would draw it smooth line, smooth, 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 okay? But I've drawn it straight lines here because it shows me something simple. So the temperature starts at 15 and goes up to 29. So it looks like the maximum temperature should be 14 degrees Celsius. But this line down here, going down from the 29 off to the right, is the speed at which it is cooling. And that rate of cooling we can use to our advantage. So what we do is this. We draw a line backwards like this. That red line there shows the rate at which it was cooling, and therefore the temperature it would have got to if it had gone straight up from here. So this is really important idea. We hope that all of the heat which is given out in a reaction is given out immediately, but it is not, which is why it follows that curve or goes up slowly. If we extrapolate, if we draw this line back, it shows us where it would have got to if all the heat had come out straight away. So this is what we do. So we try and find a line. It doesn't have to be this one. It could be slightly different, but we try and draw that backwards and back to the point above where the reaction started. So now the maximum temperature is like, that's probably 32. It's not 29. It would have been 32 if it had given out all of its heat at once. This is an important skill. It is called extrapolation. You may know the word, but this is what we're doing. We are trying to get rid of the cooling effect. That means now that the temperature rise is not 29 minus 15, but it's 32 minus 15. So it's 17, not 14. Okay, 17, not 14. Now, the rest of the calculation. So the first thing is I'm going to work out the mass of sodium hydroxide. The mass of sodium hydroxide is the mass with the sodium hydroxide minus that without the sodium hydroxide, and that gives me 6.20 grams of NaOH. 6.20 grams of NaOH. Moles is grams over relative atomic mass, RAM, relative mass, molar mass, whatever you want to call it. So that's going to be 6.2 divided by 40. Sodium is 23, oxygen is 16, hydrogen is 1. So it's 6.2 divided by 40, which is 0.155 moles. Okay, 0.155 moles. All right. So extrapolate, then start to work things out from the calculation. Look back at the question. Here it is. Plot the graph. That's worth a mark. Determine the maximum temperature attained. That is 1 or half. Determine the temperature change. That's what we've done. That's the 17. The number of moles of sodium hydroxide. That's the mass divided by the molar mass. And now use your results to determine the molar enthalpy of solution. So we've got to the point here. There's the moles of sodium hydroxide. Now, the mass of water was 108.15 minus 8, which is 100.15. So that's the mass of water. We know that the temperature was 17 degrees. We know that specific heat capacity was given as 4.18. So it is 100.15 times 4.18 times 17, which is 7116.7 joules. Joules. Okay. Then we have to divide that by the moles of the sodium hydroxide, which we've worked out up here. So we have 7.117 or 7,116 if you're using joules, divided by 0.155, which gives us around about 46 kilojoules per mole. Let's go through that again. So I'm just going back to the whole question. So here's the question. It looks very complicated, but if you do it in bits, it's not. So here we are. Plot the graph, easy. From the graph, maximum temperature. That's the extrapolation. Then the temperature change, then the moles of the sodium hydroxide. Look at the weighings. The mass of the plastic beaker, 8. The water plus the plastic beaker, 108.15. So the water is this minus the 8. The sodium hydroxide is the 114.35 minus the one with the water. Okay, so here's my graph. Extrapolate, total temperature. The moles of sodium hydroxide are the grams over the RAM, which is 0.155. Be careful how you add up these things. Then the molar enthalpy of solution. Well, what was Q? What was the heat? That was the mass of water times the specific heat capacity times the temperature rise. We were given 4.18 and we've worked out it's 17. So the total heat is 7,116 or 7.117, sorry, not 6, kilojoules. Divide that by the number of moles of sodium hydroxide and we get 45.9. And it should be negative because it got hotter. Okay. What's happening here? Come on. There we are. Okay. Now, I hope you're feeling mostly okay, or, you know, up this way. Show me how you're feeling about this sort of calculation. Oh, Osharika, it's too easy. Okay. How about St Mary's? Is this okay, St Mary's? Glory like this. Okay. St Mary's mostly like that. Dandora like this. Okay. So the thing to remember is that if you plot the graph, you have to do the extrapolation to find the maximum temperature. If you don't do that, you will lose that mark and they may then take off other marks on the way. So your problems, St Mary's, I see your problems. Okay. So I'm going to go through the question again. Okay. I'm just going to make sure that everybody understands where I'm going. So I'm going to go back to the question. I'm going to go back a bit further. Right, I'm going back to this one. Okay, I'm going back to this question. In this question, they're burning, they're using a spirit burner to heat up some water. They have 150 grams of water. There's the specific heat capacity, and it's heated from 24 to 77. The method is the same each time. You need to work out the amount of heat which is given out. Okay, that's always the mass of water. Look for that first, 150. Times the specific heat capacity. You will always be given that. Times the temperature rise or fall. That's simple. Then you have to work out the moles of whatever is reacting. In that last example, it was sodium hydroxide. In this one, it is ethanol. In this one, we have 1.3 grams of ethanol. So we need the MR or RMM of ethanol. So we have to look on the periodic table, or they will give you the RAMs for the atoms here. Carbon is worth 12, hydrogen is worth 1, oxygen is worth 16. That is worth 46. So the total amount of heat given out is 150 times 4.2 times 53. Easy. 33390. I could turn it now into kilojoules, or I could leave it till the end. The moles are also easy because they've given me the mass. I just divide it by the RAM or the RMM of the chemical. 1.3 divided by 46, 0.028. If you're the sort of person who just goes, okay, it's going to be Q over N, so it's going to be mass of water times specific heat capacity times delta T, all divided by number of moles, then you can do it all at once. On your calculator, put the moles in brackets. So you go 150 times 4.2 times 53 over, divided by, brackets, 1.3 divided by 46, close brackets. So this one came out like that. Now this one that we've just done, here's the question. It looks more difficult, but it's not. It's just a little, you have to read it carefully. So you've got a plastic beaker. They pour some water into the plastic beaker. So the amount of water will be 108.15 minus 8. So it's just going to be 100.15 grams of water. So my Q will be 100.15 times my maximum temperature, sorry, my temperature rise times what they say down the bottom, which is 4.18. My moles will be my mass of sodium hydroxide. Well, there's mass of beaker plus water plus sodium hydroxide, 114.35 minus 108.15. That gives me the mass of the sodium hydroxide. That mass has to be divided by the molar mass for sodium hydroxide, the relative formula mass for sodium hydroxide. Na 23, O 16, hydrogen 1, 40 overall. So it's going to be the mass of the sodium hydroxide divided by 40. Okay, so we drew the graph. We run the cooling curve backwards until it gets back to directly above where the temperature started when we added the sodium hydroxide. So it's 15 up to, well, this looks like about 32, maybe 31.5. I don't know. It's, let's say it's 32. So the total change is 17. So Q will be 17 times 100.15 times 2.18. Sorry, 4.18. So the moles of sodium hydroxide, well, there's the mass. It's there minus there. So it's 6.2. 6.2 divided by 40, 0.155. The total enthalpy change will be Q over N. It's always the same. So we had the mass of water, 100.15, multiplied by the specific heat capacity, here it's given 4.18, times the temperature, which we worked out from the graph was 17. There it is. 101.15 times 4.18 times 17, 7,116 or 17 in joules. I divide that by the number of moles of sodium hydroxide, and that's it. It should be a negative number. I've missed off the negative. It should be a negative number because it is exothermic. It gets hotter. Okay. I hope everybody's feeling mostly okay about that. It is Valentine's Day, so we're going to end 4 minutes early. Crazy. Oh, man. 4 minutes. I'm going to give you 4 minutes of freedom. You can run around and find roses and, oh, look, they've already gone. The rose team have already gone. Anyway, thank you very much. I hope you're feeling sort of okay. Next time will be something completely different. I don't know what yet, that you can tell me. So go out and have a good evening. Look after yourselves. And from Valentine's Day in the UK to Valentine's Day in Kenya, go and find somebody to love you. Okay? I'll say Asante Sana and Kwaheri. See you again. See you again some other time.
Bye-bye.
Bye-bye.